Hey folks, welcome back. So in this video today, we will go deeper into how vLLM works, how exactly it makes things faster and such, right? So if you go through my previous videos, you've seen that we have done a couple of tests on why vLLM is fast. In one scenario, we saw that running the same prompt with vLLM gave us the response in 3 seconds versus 19.6 seconds. And then we have this inference router dashboard that was built in my last video where we looked through the KV cache utilization and such, right? But what exactly are those things? So I'll try my best to address these things in this video. So from a very high level, we know this, right? Say when a request comes into an LLM, it has a transformer model at its core. So what it does is that it will generate a token, right? So when it generates the next token, it takes the previous token into consideration as well, and then keeps on generating further tokens, right? So it keeps doing that until the termination token is generated. So all of these things kind of happens in your memory, right? So especially in the KV cache part of VRAM. So this is a very memory expensive part, and we know running LLMs are very expensive because these GPUs cost a lot of money, right? So you need to make sure that when you're handling this process, it's very efficient. So how can you make this process efficient, right? So one option would be to batch your request. So instead of sending just one request to your GPU, make sure you send a lot of requests to the GPU so that your GPU works. Your GPU is efficiently utilized. For instance, like in this situation, if there's only one request, then you might be looking at like 0.5% GPU utilization versus when you're running your request in batch, like you might be looking at a higher utilization, right? So let's look at this example here. Say we have one NVIDIA A100 GPU, which has 40 gigs of VRAM that has a 13 billion parameter model. So a couple of things are constant here, right? So 26 gigs goes to the model weight. There's remaining 2 gigs for other overheads, and then there's this 12 gigs, which is the KV cache space that needs to be managed efficiently so that we can deal with a lot of these user requests. So if you don't know how to manage this, then there's a very limited number of requests that you can handle at the same time, right? So let's kind of understand how exactly was this done before the vLLM part. So as we can see, it says that KV cache of each request was stored in a contiguous block of memory. So say you have a request, there was a contiguous block given to store that particular request in the memory. So let's take this example, right? So assuming one token consumes 128 kilobytes of space in our memory, and then we have defined a parameter that says that maximum length is 248 tokens. So that will consume 256 megabytes of space, right? So when a new request comes in, and then assuming this request is something like, tell me all the capital cities in Europe, and let's say that request will take 100 tokens to complete. So with this setup, what will happen is for this request, we'll end up giving it the whole 256 MB of space. So see this, but it only needs 12.5 MB, so remaining 243.5 MB is wasted, and this is called internal fragmentation, right? So the thing that you need to consider here is that for each request, the maximum number of the maximum token is considered and the max space is given in the memory. So that's how it happens, and then you have this internal fragmentation issue. So taking the same example that I had above, right? So let's say if I have 12 gigs to use for my KV cache, assuming 256 is the max space that I need to give, I can only have 40 blocks, which means I can only have 40 requests at a time serving that massive A100 GPU, which is a serious waste of money and resource, right? Because we know that this GPU can handle way more than 40 requests at a time. So that's one problem, right? The other memory problem would be external fragmentation. So what happened here was that there were like other algorithms developed trying to see if they can tackle this, something like, faster transformer or the Hugging Face TZI. So what they did was that they thought, let's classify this request before they come in. Based on that, let's define this max token thing so we don't give everything 256 MB of space. So the way they did this was, say, if it's a chatbot prompt, give it 500 tokens. If it's a code generation task, give it 2048. Summarization, 1000 tokens. But this led to another problem as well. So imagine a situation, right? Say On my left, I have space for 500 tokens, and then there's this block which has been used by another request that is taking 2048 tokens, and then I have another gap that has 1000 tokens, right? But if I have a new request now that needs 1200 tokens, I will have an out of memory error, right? I can't really give this space because this is not in a contiguous block. It's in two different blocks, right? Even though I have enough free space here, 1500 token space, I can't really give it because it's not in a contiguous block, right? So it needs to be in a contiguous block. That is an important part too. So that leads to external fragmentation. So we saw how internal and external fragmentation happens, right? And the other problem here is that can't share memory. So you know the way when you ask something to LLMs, sometimes you get like 3 options, right? And then your ChatGPT or Claude will say that select one. So essentially what's happening is the user prompt is saved in one part of memory, and then all of the 3 possible responses that could come out of that prompt, right? So these guys could share the memory space of where the prompt is stored, right? Instead of copying this prompt in, or like let's say instead of storing this prompt in 3 different spaces in memory, we know that that data is constant. Like the prompt is not changing, only the responses are changed based on what the prompt was. So we should be able to share the memory, but they can't really share the memory if they don't use vLLM. So these were the problems that were kind of in the industry before vLLM was introduced, right? So vLLM kind of inspired from the like OS solution to memory fragmentation and sharing, and then based on this they came up with some solutions called like PagedAttention, right? So how exactly did they get inspired, and what kind of problem was the OS paging solving, right? So let's understand this first before we get into the vLLM thing. And just remember this part, right? So blocks are pages, tokens are bytes, requests are process. So we will come back to this later on, but then let's kind of understand the whole OS paging issues as well. And then we'll go into how it's implemented on vLLM. So imagine the situation where I have 5 and 10 used, and then I have this 3 and 4 free, right? So if a process comes in looking for 5 megabits of contiguous block, I can't really give it, and then my OS would go out of memory error. So that was the problem OS was suffering as well. So to fix this, they thought of the solution called paging in virtual memory. So what it does is that all it does is you have this memory address, which would be like virtual memory. So let's say you'll have something like a virtual page 0 that would be mapped to a certain page in your physical RAM, right? So you have your virtual address that is mapped to a physical address. That's it. So what it looks like for a process would be something like, for instance, your process would think that you are getting a contiguous block of space, something like this, right? So in virtual memory, you might get something like page 0, page 1, and then that should be page 2. Sorry about that. But then these pages are actually mapped to completely different random physical frames in your RAM, right? So these are not in same location, but we trick the process to think that it's a one contiguous block of memory, but it's actually in different locations in the physical RAM, right? So it's different frames. So again, it looks like a contiguous block for the process, but it's actually in completely different location in your physical RAM. So how is this possible, right? So to make this thing possible, we would need a page table, absolutely, because this page table will keep a record of, okay, page 0 is actually in frame 9, page 1 is actually in frame 82, and then page 2 is actually in frame 921. So we need to maintain a table like this. And then there's this physical component called memory management unit, right? So it's a physical chip that is in the CPU, which does say it will get a virtual address. It kind of does a lookup in its page table, and then it finds out that, oh, my virtual page 1 is in this particular physical frame. My virtual page 2 is in this frame. So this does all that lookup part. Of course, it will have some kind of cache, right? So that cache makes the whole hardware lookup very fast. It's called this translation look aside buffer, TLB. So process would not even know that all of that lookup is happening in the back end, right? For it, it feels like I am writing my data to this contiguous block of memory. But we know that in reality, that data has been written across different physical frame in RAM, and then we have this MMU, memory management unit, which maps the virtual page to physical page and all that stuff, right? So one brief example on this OS mapping, and then we'll move on. So imagine I have a process that needs 12 kilobytes of memory, and then we have a standard 4 kilobyte of page. So we know that it needs 3 pages, right? So you have this RAM, you just slice it into smaller pieces, right? And then how much can one piece store? So in this case, you would call that particular piece a page, and then we say that one piece can store 4 kilobytes of data. That's it. That's all it is, right? So for a 12 kilobytes to be written, you need 3 pages. So now what will happen is, for the process, it will look like, okay, I'm getting page 0, 1, and 2, and then that's the address, and I can write all of my data here. But on the back end, we have this MMU, which has a page table. What this does is that, okay, virtual page 0 is actually in that frame, virtual page 2 is in that particular frame. So process looks like a contiguous block. In reality, it's scattered across many frames in the hardware. So that's how they solve this problem, right? And then let me talk a little bit about the internal and external fragmentation here. So imagine if a process comes in and it only requests 10 kilobytes of data, right? You still have to give 3 pages. So on the third page, you would have maybe 2 kilobytes of wasted data, right? But that's okay. I mean, it's very minimal, right? So you wouldn't really waste a lot of space. And then external fragmentation is solved in a way that, see this example, right? Where we kind of chopped our RAM into different spaces. So we don't do this anymore. We will chop every single thing into 4 kilobyte pages. So, you know, like every single block is 4 kilobytes, right? So we only give what the process needs. So that's how we would solve the external fragmentation as well. And then we talked about the internal fragmentation. So now let's see how vLLM does this and how is this problem solved. So request is a process, right? That's your user prompt. Blocks are like that pages, right? So tokens are bytes, right? So imagine this prompt that says, write me an essay about vLLM in 1000 words and how it solved memory issues. So that's my user prompt. Assuming that is just 10 tokens, we have this parameter defined here, right? So these two parameters can be defined. Say vLLM config block size. So that is our page table, right? So let's say that we set that to 4 tokens, same as 4 kilobyte pages. So one block can store 4 tokens. That's all, right? For this prompt, this is 10 token. We do 10 by 4. So we need that. We need 3 logical blocks to store this. So for the request, it will look like, okay, I'm getting block 0, block 1, and block 2 to store this particular data. And then block 0 would store that series of token and so on, right? So now what happens is this block 0 is actually in physical VRAM 502 frame. 1 is in 12, 2 is in 811. So something similar as what we did previously, right? For the prompt, it looks like it's one contiguous block of space that I'm writing into, but then in reality, that contiguous block of memory, it's scattered across random locations in the VRAM. And then the only thing different here would be that in our CPU, right, the MMU, which is a hardware chip, right? So that's the hardware component that does the lookup. But with vLLM, it's a software lookup. It's not a hardware lookup, right? So block manager does that. And what it might look like in the physical chip might be something like this. So say you have physical block 12 that will have KV cache for this particular block, right? So we say that 12, okay, so VRAM 12 has logical block 1. So logical block 1 has that token. So block 12 will have that particular token. Say block 13 could be totally empty. We have this, flexibility now, right? And then block 105 might be used by a completely different user chat. And then block 502 has this particular token. Block 811 has this token, right? So see the way now that we don't need to give a contiguous block of space on the physical frame. We can chop it into smaller size slices and we can use whatever we want, right? This is, it's really handy. And then the other thing that we need to notice here is, see the way in this particular block, right, we have only stored memory issues and question mark. So it has maybe 2 empty slots, meaning it can store two more tokens, right? Because this one is storing something like, in 1000 words and how it's solved. But here there's only three different words that might take maybe two tokens. We said that one block can store four tokens, so there's still two more tokens that can be stored here. But what happens here is that when an output will be generated for this request here that we asked, right? These two empty slots will be used first before we will go and request a completely new block. So that way it will do its best to alleviate internal fragmentation. Make sure you use every single block of space, right? Instead of asking for the new one, make sure all the empty ones are filled first. So that's how internal fragmentation is kind of, it tries to eliminate it, right? There might be some internal fragmentation, but at least that's how it tries to eliminate it. So now, I had a couple of questions when I was going through this myself. Question one would be like, does the size of the word matters what the token size would be? If I have high-end responsivity, will that matter on how much it will take to store that particular token? No, it doesn't, right? So what happens is these words are converted into IDs by this component called tokenizer, and then these IDs are saved in our, it's saved in the GPU KV cache. So it doesn't really matter if your word is high or it's the longest word in the dictionary. And then how big is a token in bytes, right? So this is another important thing I wanted to know, because say we're saying that one block equals to 4 tokens, but like, my space isn't 40 gigs, right? So how do I know how much space is one block consuming? So to find that out, we can see that there's a couple of components that we need to take into consideration. Assuming I'm using the Llama 3 8 billion FP16 model, right? So these are the parameters that will be defined in the model architecture. So it's something that you get beforehand. So now there's a formula that you need to use to find the size of the token. So I took this formula, and then for this model, it turns out that one token will consume 128 kilobytes of space. So by default, vLLM has one block with 16 token of space, right? So one size of physical block will now consume 2 megabits of space. So just like how RAM will chop the physical, just like how Linux chops the RAM into 4 kilobyte physical frames, now vLLM will chop this into 2 megabits block, right? So again, it's not the entire VRAM, right? It's just the KV cache part of the VRAM. Because remember, if you have 40 gigs, then for example, if you have like 40 GB, right? Then you're given maybe 26 gigs for your model, and then 2 gigs for your extra overhead. So the remaining 14 gigs, if this is for KV cache, only this part is being used by VRAM to chop it in the KV cache blocks, right? So only the KV cache part is being chopped, not the entire VRAM. That's what I wanted to say. So assuming this, let's say 8 gigs is given to my VRAM, each block is 2 megabits block, then I can have 4096 blocks, right? So now we have all of this difference. Let's see, what kind of difference does it actually bring? Previously, max context length was defined as 2048 tokens. Max memory needed for one fully maxed out request, or for any request, would be 256 MB, right? So that way we can make 128 blocks for our, for the entire VRAM space. So even though, right, let's say our average user will only write 256 tokens, which would be 32 MB, the system will still have to give the full 256 MB for the entire life of that request, right? So the total number of requests that this model can handle with this particular concept would be, it would be the total number of blocks, which is 4096, and then divided by blocks per request, which is 128, that would be 32, right? So only 32 requests can be handled at a time if we do this particular setup. But doing this with vLLM, what happens is, let's say we have, so for our average request using 256 tokens, each request only grabs exactly 16 physical blocks, right? That is anywhere free in our cache pool. It does not need to be a contiguous block. Only the virtual part would be contiguous, right? So VRAM allocated per average request would be 32 MB instead of the entire 256 MB because of the 16 block size. So doing that, what will happen here is that, say you would have now 4096 blocks per average request is 256 token, which is 16 blocks. So that's 256 requests, right? So with vLLM, we can serve 256 requests at a time, and without vLLM, we can only serve 32 requests at a time. So that is the massive difference, right? And then if this math is a bit confusing, sorry about that, but I used this example, right? So see the way KV cache is 8 gigs, and then the total blocks that I get from here is 4096. So I took the same block and then did the calculation here. And let me know if this is like a bit messy, then I can share this in the comments as well. So yeah, thank you for watching this video.